Okay, today we're going to look at more to do with vectors. We're going to look at their components. So when we look at a vector, we can break that vector into what we refer to as components. That is the perpendicular projection, so the length of the vector onto an axis. So if I'm looking at this vector, the projection onto the x-axis would look like this. So this would be our horizontal projection, our x projection, and our vertical projection will look like this. So that would be setting at a right angle. So what we've got going on is we've got those horizontal and vertical components. So you will see me frequently referring to them as a sub y for the vertical and a sub x for the horizontal. So the process of finding those components is referred to as resolving the vector. That's where we're taking the vector and we're resolving it into its individual parts. So if only the components are known, there is a way to recover the original vector. So let's think about this logically. If I only know the horizontal and the vertical piece, I could find the resultant vector by basically finishing off that piece of the triangle, since those are at right angles, and I could use basically my Pythagorean's theorem. So let's break this down into what we can do with our angles here. Hold on. So if I look at this piece as my angle theta for this vector, and I'm just going to call this vector A as it was on the last slide. This is our horizontal piece. This is our vertical piece. Now you may remember from trig class, SOHCAHTOA, some old hag caught a hot tamale over Arkansas. So if I'm looking at sine of angle theta, what that tells me I'm looking at is the magnitude of the opposite side, so that would be a sub y, over the hypotenuse, so that would be the magnitude of vector A. Cosine of our angle theta would be my horizontal component over the magnitude of the hypotenuse, so the magnitude of our vector A. Tangent of that angle is going to give me opposite over adjacent, so a sub y over a sub x. Now, why is all of this important? Because if it comes down to push comes to shove here, my horizontal piece is going to be the magnitude of my vector times cosine of the angle at which it goes. Now remember, to have a vector, we have to have a magnitude and a direction, and we always use that angle from the positive x-axis. To get the y component, we have a sine of theta. And I'm sure by now you're wondering, why did I throw this tangent in here? Because if I only know the horizontal and the vertical components, I can find theta using my inverse tangent feature. So using arctangent of a sub y over a sub x. Now you do have to be careful. Right now we are currently in degrees, so your calculator needs to be in degree mode. Now you may say, but wait, I can't graph that way. And no, you can't, because in order to graph, your calculator must be in radian mode. So the final piece to this puzzle is, how are we going to find the magnitude of vector A if I only know the horizontal and the vertical components? Well, we are going to go back to our good friend, the Pythagorean theorem. So A is going to become the square root of our horizontal component squared plus our vertical component squared. So this is taking us to the idea of a unit vector. A unit vector is a vector that has a length of 1, and it's in a given direction. Now there are 3 that have very special names. There's I hat, which is a unit vector of length 1 in the x direction, that is the positive x direction. There's j hat, which is a unit of length 1 in the positive y direction. And then there's k hat, which is a vector of length 1 in the positive z direction. Now, as I've said before in class, these have been shown to be slightly different if you look at different textbooks. So in the world of math and in the world of physics, I have seen them these different ways. Now I am going to stick with I hat, j hat, k hat, just for the simple reason that we have enough x's running around on their own. We don't need to add any more to our equations. We just don't need to go there. So we're going to stick to the physics convention of I hat, j hat, k hat. And yes, this caret over the top is read as a hat. So we are using a right-handed coordinate system. That is the world that we live in. So that means our x would be off and to the right, our z is coming out of the page at us, and our y is up. So when we look at unit vectors, these are useful for expressing other vectors. So we can break a vector into its constituent components. So if I have a vector, let's say A here, we could say, okay, well that is maybe 4I hat plus 6J hat. Well, what does that tell me? Well, that tells me I'm 4 in the X direction, 6 in the Y direction. And that allows me to be able to calculate the magnitude and the direction of my vector A. The other thing that putting vectors in unit vector notation does is it allows you to easily add the vectors. We don't have to graph them and hope that our angles are just so. So if I have vector A here and I have vector B here, in order to add them together to get A plus B, I'm just going to line them up here. So I'm going to have BX I hat, BY J hat, and BZ K hat. So if I add down my vector R, which is just vector A plus vector B, is going to be, I add like components. Now you may be saying, what do I mean by like components? These I hats are alike. So that means I'm going to have the X components times I hat, the Y components, J hat, and the Z components, K hat. So it allows a simple addition process that doesn't involve a protractor and a ruler and very careful parallel behaviors. So here, if I look at this image and we look at our signs. Now, right now, in D1 is moving towards the positive X direction. So the signs for the X components for D1 is going to be positive. The sign for D2 is also going to be positive. It's still moving off and to the right. Now, if I look at the Y component signs, D1, we are moving up. So D1, we have a positive sign. D2, you'll notice that D2 is starting to move down vertically, so D2 is going to have a negative sign. But what about that resultant vector? Well, if I have a vector that goes from where I start to where I end, you're going to notice it's going to go to the right, so the X component is going to have a positive sign. The Y component, we are still going up, not as quite as far as D1 did, but the Y component is also going to be positive here. Okay, so if I wanted to plot some of these vectors, I'm going to first kind of put a rough scale here. So that's 1, 2, 3, 4, 5. 1, 2, 3. Okay, so for our first one, we are going 4.2 in the x direction, so about right here. And then we are going down 1.5 in the y direction. So my vector is going to look pretty much from where I start to where I end. So about like that. That would be vector A. Vector B, you'll notice, is negative 1.6. So about right in here. And then it goes 2.9 in the j hat direction. So almost right about here. So that vector is going to go from where you start to where you end. So it's going to look something like that. Now C is just straight negative 3.7 in the y direction. So we are going to go straight 3.7 down. So it's 1, 2, 3, about 0.7 right there. Now if I wanted to find their sum, now I could do it graphically, yes. But that's not as nearly as much fun as what we're going to do. So here we go. Vector A is going to be 4.2 I minus 1.5 j. Vector B is negative 1.6 I plus 2.9 j. And vector C is straight negative 3.7 j. So we're just going to add down. So their resultant R, all of these vectors added together, is going to be so I'm going to have 4.2 minus 1.6, so that's going to give me 2.6 I hat. Then for our y components, we've got, see, that's going to be a positive 1.4 minus 3.7, so it's going to be negative 2.3 j hat. So my resultant vector is going to start where we initially are. It's going to go over about 2.6, and then it's going to drop about 2.3. So my resultant is going to look like that pink vector right there.